Hi, my name is Juliet, and I'm the creator and host of Connecting the Dots podcast. I love ideas and problem solving, and my career in communication has led me down a path of curiosity. Why we do what we do, how we tell better stories, and how African scientists solve everyday problems. Join me on this enlightening and entertaining exploration of African science like you've never experienced before. Get ready to laugh, learn, and be inspired. Hi, welcome yet again to another episode of Connecting the Dots podcast with me, Juliet. Today, we are going to be discussing genomics and bacteria. So, microorganisms like bacteria have been considered the first living organisms on Earth. They have been on the Earth for the last 3 billion years. And fun fact, the number of bacteria in your mouth is more than the total number of humans on Earth. And to tell us more is Professor Iruka Okeke, who is the professor of pharmaceutical microbiology at the College of Medicine, University of Ibadan in Nigeria. She has devoted her career to studying how bacterial germs inherit traits and how they spread them around. She's interested in bacteria. I dare say, not interested only, but very, very excited about bacteria that causes diseases as well as bacteria that become resistant to drugs that are used to treat infections. Professor Okeke is committed to finding solutions to strengthening laboratory medicine in Africa, and she is an editor and award-winning African scientist in microbiology education. In addition to being a celebrated educator, she is also the author of 2 books and several scientific publications. We are very delighted to have you with us today on the podcast, Professor Iruka. Welcome.
Thank you, Juliet. Thank you for having me. I'm really excited to talk to you today.
And Iruka, tell us a little bit about your background, your upbringing, as well as your professional career life.
Okay, so I'm the second of 4 children. I went to Queen's College, Lagos, which is one of the best girls' schools in the world. And I think definitely better than your school, whatever it was, Juliet.
Yeah.
The nice thing about going to a school where there were lots of ambitions for us was that we could play around, learn things, not be threatened. And I got really interested in biology in school. I actually won the biology prize at the end of high school.
Wow.
When I finished high school, I went to pharmacy school. Then growing up in Nigeria, there was this impression that you should do a professional degree, be a doctor, be a lawyer, be an engineer. None of those really fascinated me. Pharmacy sounded interesting. I thought you'd be mixing things to make medicine. It didn't occur to me then that I could have a career in science. So I went to pharmacy school. In pharmacy school, what I really enjoyed was the biology and chemistry. And I think it's there that I learned that, well, I could do a postgraduate degree, become a scientist. But even then, I wasn't fully convinced. I chose to do a master's in pharmaceutical sciences, thinking that I would work in the pharmaceutical industry, be involved in quality assurance of medicines or that kind of thing. But when I started the master's, I realized that my interest was really in asking questions. I loved playing around with things in the lab and setting up an experiment, testing hypotheses. And so when I finished my master's, it was sort of natural to go into a doctoral program and do a PhD. I had the benefit of 2 amazing graduate advisors. My undergraduate, master's, and PhD was supervised by Professor Olamikora, who recently retired from Obafemi Awolowo University. And part of my PhD was co-supervised by Professor Jim Capra at the University of Maryland. So I spent 9 months of my PhD in Maryland and did sort of a sandwich PhD. So yeah, that's basically how I started from a girl growing up in Lagos to a scientist. Of course, many professional positions before I eventually moved to Ibadan.
And Iruka, the first time I met you, the thing that struck me the most was how you were very quick to say how you love bacteria. In fact, if I recall correctly, your statement was, "Hi, my name is Professor Iruka Okeke and I love bacteria." What is it that fascinates you about bacteria?
I mean, it's true. I do love bacteria. I'm in this job because bacteria are so fascinating. It's true that I can do this and then make impact in health, but I'm really driven to wake up every morning because the bacteria are so beautiful. So what do I love about them? I mean, you said it yourself. They were here before we got here, and they'll be here after we leave. So they're ancient in that way, but then they're so simple. And they're also beautiful. I mean, you put them on different types of media. They have different colors, different shapes of the bacterial colonies. You look under the microscope, you see the shapes of the bacteria. They're interesting biochemically. And because they're simple, you can actually see them do one thing at a time. I mean, most of the things that E. coli can do, humans can do too. But the human cells, there's so many different types of them. They're doing different things at the same time. It's difficult to follow. But bacteria, there's some simplicity in the complexity that makes them really fun to study and fun to teach you too. And I teach a lot.
Sorry, continue, Iruka.
Yeah, I was saying that they're beautiful to look at and to work with, but because there's simplicity in the complexity, they're fun to work with and they're also fun to teach with as well.
What's your favorite bacteria, if you have one?
It's definitely E. coli. E. coli is an intestinal bacterium.
Yeah.
Most E. coli just live in our intestines happily with us. They're what we refer to as commensals. That is to say, we benefit and they benefit from them being there. A few E. coli are harmful. They're really, really tiny minority. And unfortunately, they get all the press. You'll see a newspaper headline that says, child dies of E. coli or something like that. But that's actually a minority of the strains. The majority are actually commensals. And E. coli have a very simple biology, such that many of the things that we understand in bacteriology and even in biology came from studying E. coli.
Iruka, in a previous podcast, we interviewed one of your Callisis Juma fellows, Professor Joanne Passmore, and she was talking about bacteria and the good bacteria and the bad bacteria, her focus being vaginal microbiomes. In your case, it sounds like the intestinal bacteria are what you want to focus on. Why is it such an issue? And when you talk about news headline grabbing coverage that says child dies of bacteria, I mean, you are absolutely correct that they do get bad press, but why is that the case with bacteria, especially intestinal bacteria?
Yeah, so the intestine, it has the largest number of bacteria of any niche in our body. There's a wide range of bacteria. As much as E. coli is my favorite, and all of us carry a lot of E. coli, there are many more bacteria in the intestine that are anaerobes, that is, they can't survive in the presence of oxygen. And these are all very interesting. They protect us from disease. They actually shape the way our bodies develop. And there's a huge number of scientists that are studying what is known as the normal flora or the microbiome, what should be in your intestine when you're completely healthy. These are organisms that determine whether we are heavy or light. Sometimes they determine how our nervous systems develop and so on. Now, I'm in particular interested in bacteria that belong to a family that includes E. coli, that are mostly harmless, as well as some other bacteria that can cause disease. So this includes the E. coli that cause disease, things like salmonella, which you may have heard of.
Yeah.
And these are organisms that can cause disease, first of all, in the intestine. Young children in African settings are often infected with E. coli or other bacteria that will cause diarrhea. And for adults like you and I, if we get that kind of diarrhea, it's kind of a minor illness, something that might be irritating, makes us step out of a meeting to go to the bathroom. But for a young child to get that kind of diarrhea in their first year of life, first of all, it's potentially fatal unless they are rehydrated. And secondly, it can interfere with their development. So that's the first thing. The other thing is that these bacteria come in normally into our intestines because we eat them and drink them. But some of the bacteria that can cause disease can invade from the intestine and get to the bloodstream. And when they do that, they cause very, very serious infections, bloodstream infections like bacteremia, Salmonella typhi. If you eat that, please don't eat that. You can get typhoid fever. So I'm interested in those bacteria that look and act like E. coli, but can also cause disease. And we're really trying to understand what is it about them that makes them disease-causing when they're so similar to the organisms that live with us harmlessly? And then secondly, when we understand how they cause disease, can we also design ways to protect ourselves against these infections? And then another thing about these bacteria is that they change naturally. And because they change naturally, they have the opportunity to evade some of the tools that we develop.
You've talked about how the bacteria changes naturally, and one of the things that we have uncovered for the work that you're doing is your focus on genomics. So, what are some of the things you found out about the DNA of bacteria that the public would be surprised to know?
Gosh, where do I start? Well, I mean, let's talk about change, for example. Sometimes bacteria can just change one letter in their genetic material and become resistant to an antibiotic.
Mhm.
Such a small change, but it has such a big impact on clinical care. Sometimes bacteria can exchange DNA. So one bacterium that has become resistant can share the DNA that has made it resistant with another organism.
Mhm.
So in fact, even though change is something that is rare and uncommon, bacteria can rapidly gain new functions, including resistance to drugs, just by sharing after changing.
And Iruka, you've talked about drug resistance, and we've talked about bacteria having been on this earth for billions of years. We know that it's only recently, in the last century, we're looking at the 1920s, when antibiotics were discovered to be able to deal with some of the diseases that are as a result of the bacteria. Can you talk about pre-antibiotic, what happened in the era of antibiotics and now with drug resistance? What's your take on this and how should we address the antimicrobial resistant grand challenge?
Yeah, antibiotics are a huge miracle. People would have things like a minor scratch and then they'd get infected and then they would die. These are the sorts of things that happened in the pre-antibiotic era. Someone would have to have a cesarean section and then that would get infected and then that would be the end of that mother. So I think having antibiotics has really changed how medicine is conducted, but also our ability to survive. I'm sure all of us can think back, almost all of us can think back to a time when they had a severe infection, which they may or may not have survived if they didn't have antibiotics.
Right.
Now, before antibiotics, that's not to say that all of us died. I mean, there were human beings on Earth when antibiotics were discovered. But I think more of an effort went into finding what we would now refer to as alternatives to antibiotics because people didn't have a choice. There was a lot of care about developing vaccines, for example, to prevent infections because it was known that infections were so deadly. And so antibiotics, in a sense, made us a little bit lazy. We didn't think about how to avoid infection because we knew that, well, if infection comes, I can handle it.
An
But
antibiotic.
when you think about the fact that in North America and Europe, everybody has pipe-borne water, everybody has good sanitation. And the reason for that was the way to control infection before antibiotics came about. So now that we have antibiotics, when we make a lot of advocacy for good water, sanitation, and hygiene in places like Nigeria, where I live, there's less of a push because it's known that, well, if someone gets typhoid, there is still the option of treating them with antibiotics. Now, unfortunately, that option is going away. The bacteria are becoming resistant to the antibiotics. We're not developing new antibiotics fast enough. And so what that means then is that we have to start thinking back to those tried and true measures that can protect us against bacteria before they cause infection and help us live healthier lives.
And Iruka, I want to ask you a question we asked our previous guest from Drugs for Neglected Diseases Initiative, Professor Sam Karaoke, who shares similar interests to you on antimicrobial resistance. Do you think or feel that the world is in crisis, and what concerns you around AMR?
I think, first of all, I mean, Sam, really great work done in the last 3 decades when people were thinking only about malaria in terms of fever in children in Africa. Sam was one of the first people who said, okay, malaria is there. We know it's there. But there's other things like typhoid and other bloodstream infections that cause disease in young children as well. So, yes, we are in a crisis at this point. So as I mentioned earlier, we've almost run out of antibiotic options for many patients, and we're not developing new drugs fast enough. So this means that if we don't do something to control antibiotic resistance, we could find ourselves back in the pre-antibiotic era. I think in the last year or so, the awareness has increased quite a bit, not enough, but quite a bit. If you've been following the news, you will know that both the World Health Assembly this year and the UN General Assembly had antimicrobial resistance front and center on their agenda this year. There are a lot of recommendations that experts made that were adopted at the UN General Assembly. And so we hope to see now countries working towards targets such as reducing the deaths from antimicrobial resistance by at least 10% by 2030, reducing unnecessary use of antibiotics in humans, which is a major factor that is driving antimicrobial resistance, reducing that by 20% and reducing unnecessary use of antibiotics in animals by 30%, all by 2030. So this is what the UNGA signed on to just about a month ago.
I really liked your formula, the 10, 20, 30, and very memorable, by the way, by way of phrase that the public can remember. What would an ideal world look like if we all really put the 10, 20, 30 into practice?
Yeah, I think things would be a lot safer for our children. Okay. If we can do 10, 20, 30 by 2030, which is really how it was said. Yes, it is a catchphrase that we hope that all of us will remember. Then the antibiotics we have now can be conserved for the next generation.
Right.
So that's the first thing. And then secondly, there's going to be the opportunity to push forward the development of new antibiotics. And when I talk about new antibiotics, one of the things that we in Nigeria and elsewhere in Africa are afraid of is that although the pipeline is very small, the things coming out of the pipeline are not things that we would easily be able to deploy here. So we need drugs that will be inexpensive, easy to administer, easy to store. And the newer antibiotics are not that. So we're hoping that this will be a push to develop more antibiotics, but also antibiotics that can be used in the least resource settings. And in addition to that, it's not just antibiotics that we need to develop. We need to develop vaccines to prevent infections. We need to develop better diagnostics so that we know who needs an antibiotic and who does not. And then finally, it's very important to be aware of the fact that there are innovations that are available here today. Things that can help us improve infection prevention and control, things that can help us improve water, sanitation, and hygiene, vaccines that already exist that should be deployed. And I think implementing those things will make us healthier in addition to doing something about the problem of antimicrobial resistance.
When you look at bacteria and AMR, who are the people who are most affected by bacterial diseases and AMR?
The answer to that is quite sad because, people talk about misusing antibiotics and how this fuels antimicrobial resistance, and this is true. But the people who are most affected are people who don't have access to antibiotics, who can't use the new drugs. A number of people who die of antimicrobial resistance infections are neonates, children that get neonatal sepsis in their first few days of life, and they've never taken an antibiotic in their life. So neonatal sepsis is essentially a severe bloodstream infection and the body's reaction to that infection that occurs in a newborn baby. And some babies get infected right before or as they're being born. Other babies get infected within a healthcare facility. And then that bloodstream infection, their new bodies try and fight back against it. And then the whole fallout from that is potentially fatal. If you want to treat that, you need to be able to detect it very early and make sure that the first antibiotic that you give is the right one. So we've seen a lot of progress with child survival in Africa. The deaths among children under 5 are dropping. And this is really good news. But actually, the deaths among children under 1 month are not dropping. So we need to do something about neonatal sepsis. And the reason why they're not dropping is because of antimicrobial resistance, because we can't be sure that when we give the first antibiotic that it's going to work.
So that last bit, when you've just talked about you cannot give antibiotics because you worry about resistance, is that because the resistance is from the mother to the child, or is it you're worried that the child will not be able to be cured by the antibiotic that you provided?
Okay, so ideally, if a child had neonatal sepsis, you would use an antibiotic and the child would get better. This does actually happen for many children that have neonatal sepsis. Now, if the bacterium that is infecting that child is resistant to the antibiotic that you give, then you'll discover that 2 days later when the child is even sicker. And then you try another antibiotic. And by then, the chance that the child will survive is quite slim. So if you want to avoid that kind of situation, first of all, we've got to avoid children getting infected in the first place. We've got to make sure that the places where children are born are pristine. As I mentioned, some of the infections come during birth from the mother, but some of them actually come from the healthcare environment. So we need to get rid of those ones that come from the healthcare environment. The second thing is that we need to understand antibiotic resistance patterns in particular geographic areas so that our first choice of antibiotic is likely to be right. And then the third thing, I think we have to up the types of diagnostics that could be available so that when a baby has signs of potentially having neonatal sepsis, very early on, we'll be able to say, oh, this is what's causing it. This is what it's sensitive to. This is what I should give.
We've heard you talk about how there's the improper use of antibiotics, especially when it comes to using them for things like mpox, which is such a big problem at the moment. Just taking you back to genomics, by reading the DNA of bacteria, scientists can pinpoint the mechanisms that enable resistance. So allowing for faster identification and potentially more effective treatment strategies. In your study of the DNA of bacteria, how can scientists use genomics to really address this AMR crisis we are in?
Lots of different ways. So first of all, everything an organism can do, including a bacterium, is written in the DNA. So if I read the DNA of a bacterium, I immediately know what the name of that bacterium is, what potential diseases it can cause, and what antibiotics it's resistant to. So imagine a situation where a patient has an infection. If I can read the bacteria, the DNA of the bacteria while that patient is sick very quickly, I know everything I know to be able to take care of that bacterium. Now, currently in today's technology, we can read the bacteria that are causing infections, but we do it too slowly. So we're really working to see whether we can speed it up so that it can be done within the lifetime of an infection so that we can do something about it while it's causing disease, rather than to read it later and say, oh, that's why that happened.
Right.
So that's one thing that we are trying to do. The other thing is that increasingly bacteria are being sequenced for surveillance so that countries know where they are in terms of antimicrobial resistance. So those sequences that are read and then banked, we're looking at them again and then asking, well, what are the most common causes of this infection? What are the things about the bacteria that are causing this infection that could be deployed for vaccine development or for drug development? So essentially repurposing these sequences that are generated actually at quite a large cost so that we can get more information out of them, more than just what's causing the disease and where is the disease. So we're doing all of those things. And of course, making sure that we're teaching scientists to be able to read DNA. Currently in undergraduate curricula across the world, not just in Africa, very little is taught about genomics. And I think we have to teach a bit more so that younger scientists can do more with the sequence as we generate it.
And Iruka, that's an amazing segue to the question I was going to ask you about the challenges in your area of work. Why is that genomics is not well taught on the continent? And as you speak about that, I'd love for you to talk about genomic surveillance, especially your work with the Nigerian Centers for Diseases Control.
Yeah, so first of all, most of us worldwide teach the way we were taught. And so the original curriculum, all the way back to Socrates, it's been really slow to change the curricula over time. But there's certain ways, for example, genetics. Anybody who's taken a genetics course in university typically started with Mendel, Gregor Mendel, and his peas. Very important part of genetics that still needs to be taught. But you spend so much time talking about Mendel and his peas. This is like 1/4 of the course. And then towards the end of the course, you just mentioned that, oh, by the way, in 1953, Watson and Crick discovered the structure of DNA. Yeah. And by the time you get into this is how to read DNA in a sophisticated way, it's time for the exam. And the students have moved on. So we really need to reshape our courses to recognize that students today have a lot more information that they can get online in a way that students of Socrates did not have. And then make the Mendel lectures shorter so that we can actually teach students hands-on, getting their hands dirty with DNA so they actually know how to read it by the end of the course. So I think we've been even slower in Africa to update our curricula, in part because our instructors are pretty overwhelmed. My classes are huge. We have a shortage of PhDs in my institution. So the time that one needs to innovate is often not there. The other thing is that the instructors themselves haven't had a chance to learn how to read DNA in sophisticated ways. And so we're going to think about ways to make it easier for them and easier for the students to be able to leapfrog over the curricula of the 1980s, 90s, 2000s to what should be the curricula of today.
And Iruka, I can only imagine as you talk about the few PhD postdoc students that you have, majority of them might be male. So, we've had you mention before that microbiology tends to be a bit of a boys' club. As an African woman, what have been your greatest lessons on staying the course?
It's interesting that you mention this. If you look at undergraduate classes in microbiology, genetics, molecular biology, you often find that actually there are more women these days than men.
Oh, wow. Amazing.
But when you look at the leaders in the field, you see mostly men. And so I think we really have to understand why it is that women start out with an interest in science
And drop off.
and somehow don't make it to leadership. I'm sure you've heard this phrase before in global health that women do it, men lead it. So there are lots of women at the bottom of the ladder. And I think what we need to do really is to hoist them up. There are a lot of things that happen early in the day that prevent women often from becoming leaders. Some of those things involve the fact that, your postgraduate training takes place typically in your early 20s, whatever your gender. And if you're a man in your early 20s, there's a good chance that you're either single or you're married to somebody who's having babies. If you're a woman in your early 20s, there's a good chance that you are having babies.
Right.
And having babies and being able to balance a graduate program can be a pretty challenging, particularly in African settings where finding safe and quality childcare outside of the home can be difficult. You have a number of responsibilities within the home. And I think we have to be flexible about how academia is set up so that women who find themselves in those sorts of situations, but who want to be able to develop themselves so that they can be leaders, have the opportunity to do so. There's no rule that says it should take 2 years to get a master's degree, but most master's programs kind of mandate that. But if we allowed a woman to take 4 years to do a master's degree, then she might be able to balance that with other things that she's doing. So I think these are things that we have to think about. And then just really basic things. A lot of my students and contemporaries, when I got to universities, I found that they were just kind of taught, not explicitly, but implicitly, that mathematics was a thing for men. I was really fortunate to go to a girls' school. So, everybody just sat down and did the mathematics. But a lot of people thought, mathematics was kind of a boys' subject. And so even there, you're whittling away the women who could potentially become scientists. They're often choosing what people will refer to as soft sciences, like biology, because there's less mathematics.
Mm-hmm.
Whereas when it comes to molecular biology, there's a lot of mathematics in molecular biology. And so if you haven't had a good mathematics foundation, you might be more reluctant to take upper level courses in molecular biology. And that's where you're going to learn to read DNA.
I think there's a lot that has to be said about the stereotypes that we introduce in science. And, it's really exciting, even for me, to have a lady like you doing hardcore science, or what people might feel is hardcore science. When I listen to you, you make it sound so simple, but simple and fun. And we've been talking on this podcast about role models. So I want to ask the question I've asked previous guests. And like I mentioned, Professor Sam Karaoke, really, when we asked him the question of who are the African scientists you look up to, your name popped up very quickly. So to you, the same question, who are your top 3 very quickly? African scientists you look to, who are they, where are they, and what are they doing?
Did I only have 3? Gosh, I have like 30. I mean, I'll start with Professor Adebayo Lamikora. He's retired, but still working and trying to build institutions in Nigeria. He mentored a lot of us as we were growing up in science. And unusual for the day, a lot of his mentees were female, and a lot of us are leaders in our field. A lot of my contemporaries Isabella Oya in Kemri and Mainga Hambula, they're both in Kemri. They're doing really fantastic work on malaria and clinical trials building. Some of the people that are role models and I look up to are actually younger than me. I watch Yao Bediako's work very closely because he's moved out into the private sector. And I think we have to do this in Africa if we're going to build a scientific community. So I think that was very brave and he's doing it in a really high quality way. So that is, again, another person that I look up to. Abdoulaye Jimdi in Mali, he was a postdoc when I was a grad student, and I wanted to be him when I grew up. So, I mean, I think there's so many of them across the continent, older scientists, younger ones. When I moved to the University of Ibadan, I was actually very impressed with work that Chinedum Babalola had done here. She's still based here, although she's on a secondment as a vice chancellor elsewhere. But she built a chemistry lab here that can compete with anything anywhere in the world at a time when everybody was saying it's impossible to do science in Nigeria. And that was one of the things that motivated me to come back and start my program at the University of Ibadan.
What are the things that scare you and excite you about our world today?
I think one of the things that excites me is that the type of progress we're seeing with infectious disease science in Africa now is unprecedented. If you remember what was referred to as the genetic revolution, the molecular biology revolution that started with Watson and Crick, Africa didn't see much of that.
Right.
But now we're in a genomic revolution where, I mean, in the COVID pandemic, look at what scientists like Tulio in South Africa and Christian Happy in Nigeria did. They sequenced so many genomes. They discovered the evolution of the Omicron variant for the rest of the world. So I think we've seen an enormous level of progress in genomic sciences on the African continent. And this is something that really, really excites me. It's really wonderful to be part of that revolution. And I think what scares me most is the potential or the possibility that this won't sustain. And so I think what we really have to work hard about is ensuring that we can hand this to a next generation that will really take it to flight. And so I'm very particular about mentorship. I'm asking the questions about why it is that promising young scientists in Africa are finding it difficult to stay here and work here. I don't have answers to those questions, but I'm asking them because they're really important. And this is the way that we're going to sustain this revolution and move it to the next level.
Iruka, thank you so much for all the work that you do. Very impressive work. You know, you inspire us. And as we wrap up, what is your parting shot?
I'd like to encourage all of us, people, governments, hospitals, to make the most of innovations that science already has on the table. There are innovations that can help promote infection prevention and control in hospitals that will prevent mothers and their infants getting sick when they're in hospital. There are vaccines. I mean, there's a typhoid vaccine that is enormously effective and has been given to every child in Malawi. And it hasn't been deployed in Nigeria, which is such a bigger country with a bigger typhoid problem. So I'd really like to encourage us to use scientific innovations that are available. This will also encourage those of us who are doing science to develop new things. Because one of the things one is often afraid of is that, you know, you might discover something and it would never leave the lab.
Iruka, like I said before, you inspire us. We're excited to see the work you continue to do with bacteria. We wish you well on your research and your journey, and kindly please continue being the global health ambassador that you are and the global health leader as well. Thank you so much, Professor Okeke.
Thanks for having me, Julia. It's been really a lot of fun having this conversation.
Thanks for tuning in to Connecting the Dots podcast, created by me, Juliet. This episode was brought to life by Mumbua and Kevin at Silent Global in Nairobi, Kenya. If you enjoyed this episode, don't just keep it to yourself. Share it. Tag us on CTD Pod Africa on all platforms. Keep the conversation going. Let us know what you'd love to hear about. And join me on the next episode as I interview the next amazing scientist here on Connecting the Dots podcast.